writing to you the background study this material, and then I'm going to show the crystal structure of it. So there is of course a difference in crystal structure. It was made. Okay. All right. So. What is Herschel alloys? There is Herschel alloy is that the energy band range can be adjusted between 0 and 4 electron volt. It is very important because for technological application, this is very important for us, because we have some physical properties, crystal structure properties, the property changing by the dopant element are, just essential to optimize the system. So in the literature, we have some data in the form of iron, 2, mangan, and germanium. This is this is not in cubic form, but for the cubic form of the cubic form is very important and a strong candidate for spin transfer torque. And for other applications. So in the literature, what we have just hexagonal form of the material, but in this study, at the first time, we investigated the structure, morphology, and magnetic properties, doping vanadium to the system. And then Herschel alloys obtained by arc melting method were studied too. The results were evaluated under highlight of the provided data. So at the left-hand side of it, right here, this is in literature, we have this structure. This is hexagonal in the form of iron, 2, mangan, and manganese and germanium. So it has a lattice parameters like this. This is a good candidate for technology application, but the problem is for RAM application, it has to be in cubic form. So in our study, we try to develop a material to make it similar properties or improving the properties by adding some extra elements to make the structure cubic. So what we did here, right here, let me show you. This is our system. We add some vanadium to the system and we change of it and as geometry to understand the effect, what kind of effect we have and what is going on in physical properties. So the system is now cubic, and the space group of the system is P63 mmc. And the alignment of the system was made by current software. In preparation part of the Herschel alloys, we use iron, vanadium, manganese, and germanium chemicals obtained from Sigma Aldrich, were synthesized by arc melting method. We just mix them in appropriate proportion for final Herschel alloys. So in order to obtain homogeneous structure, we use melting process for 5 times. This is very important because less than 5 times gives us not a homogeneous structure. It was tried by us before. And in argon gas environment, the obtained sample were subject to heating and cooling treatment by applying a specific heat and cooling procedure. That is right here. So we started from heating from the room temperature. The system, material weighted like there is a minute in a term of minute, and we exited room temperature here. So this is our specific heating and cooling treatment. So at the first time, the sample were heated to 900 degrees centigrade at the rate of 2 degrees centigrade per minute and kept at the temperature for 5 days. Then the samples were released for cooling process without any programmed decrease in furnace. This is our excited pattern at the right hand side here. And there are 3 samples here. One of them is given by the blue color without manganese. The second one is we added manganese like 0.75. The third one is given with the black color. We just add 0.5. from manganese side. And we got the XRD properties of it to understand if we have some extra fixed or not. The XRD patterns of the vanadium doped iron 2 manganese germanium cubic compound we obtained by arc melting method. So we just have here some little peaks. So the contribution of the little peaks are not that important for the overall results. Here, this is the concentration dependence as implemented per matter. What happens, it starts from the zero right here. And we increase the concentration to 0.5 and 0.75 here. You see this implemented per matter, and it is directly increasing like this by adding vanadium to the system. This one is out of plane lattice parameters, that is decreasing like this. So the system is like exotic material. Here, we have to understand first of all the stoichiometry of the materials. Therefore, we got some EDAX and the SCM pictures. The surface is, a little bit creaky. There has some porosity on the surface. This is because of the, polishing of the surface. And then you see here the amount of material, the atomic percentage here. So the formulation, iron 2, vanadium, and germanium is right here. So we provided the stoichiometry. The right-hand side here, we also provided the material given by the amount here. So given the colors here, for iron, vanadium, magnesium, and germanium also different from each other, and the colors also showing that after polishing the sample, we still have the materials too. This one is the last sample with the stoichiometry of 0.5. What we get here, the surface morphology and elemental composition of the material, just like alloys, where you see depicted on the figures. In all SCM image, some holes, we have some crack type formation we observe. This should be reason of sanding, smoothing, polishing, and heat treatment before taking the SAM image. Also, the colored SAM pictures were also showed that the elements belong to the composition were still exist after the heat treatment. So the heat treatment is not affecting the material, just improved with the physical properties of it. Actually, the gist of the study is right here. We didn't know before taking the magnetic properties. So this is, we see the important part here. So this is the magnetic properties, magnetic field dependence, and magnetic moment used at 5 Kelvin in all three pictures, given by the black color. In all three pictures are given us ferromagnetic behavior. But when you increase the temperature to 300 Kelvin, 400 Kelvin, so the system is turning itself to paramagnetic system. But one more important thing here is, in low temperature, like 5 Kelvin, the system is very easily align itself. It means that when you apply the magnetic moment, the system is turning itself. So it is very important for spintronic applications. So we got temperature-dependent magnetic moment. These are all taken under 20 Kelvin, 20 kilo magnetic field. The temperature-dependent moment variation of the Hertz alloys obtained by arc melting under 2 Tesla. Zero field cooling, ZFG, and field cooling, the FG curves, match well and depict a general decrease in the moment values in increasing temperature. This behavior is partly consistent with the Curie law after the temperature 200 Kelvin. A summary. First of all, we got the most intensive peak at 2 theta equal to 51, almost 51 degree for 2-0 plane in XRD. So almost there is no secondary phase. So This is matching well with the literature. The lattice parameter were calculated as like this, as you see, and then it can be said that random structures are formed on the surface, especially where 20 macron image annealing effect is combined with 3D island atoms. The magnetization MH curve, due to the magnetic field taken at the temperature of 5 Kelvin, creates a negligible coercive field, while at the 300 Kelvin and 400 Kelvin, there is no coercive field, and the ferromagnetic properties of the mid samples are lost at this temperature. And also, the importance of the study is, even with a little amount of magnetization, the magnetization shows alignment easily. Thank you very much for listening to me.
Okay, thank you for the presentation. Is there any question in the audience?
Such materials, the temperature, that say critical temperature, magnetic to ferromagnetic transfer. Yeah, 200 is the critical temperature. The fair change. 200. 200, yes. You see, let me show you the picture again. Here, right here. So this part is not that important for us before 200, but after 200, you see the system is changing its magnetic behavior. So 200 is the critical temperature.
I have a curiosity regarding the central graph. Why is it that the zero field cool is above the field cool in this case, while in the other ones?
Well, actually, it depends on the vanadium. You see, the formulation is different. So we have just vanadium 1 here. Vanadium is 0.75 here. Vanadium is 0.5 here. So it makes a difference. One more reason we have that is actually because of the process. Process makes the system a little bit, turning itself. Maybe improving the effect, you can say.
Okay, I understand. Is there any other question? Then let's thank the speaker again and hear you.